software and a demonstration of how understanding history is important, how framework and starting points matter. So effectively, one of the trends in the software industry was rapid application development. Now, rapid application development means you just start developing code, right? You don't design it, you just like whip it out there. And the original way they did this was with sort of very high level, very simplistic languages. And the reason why they did it this way is because the purpose was not to develop the software in that language. The purpose was to get a working mock-up of a piece of software so that the business people could try it. Now, why was this important? Because the fundamental problem in software design has always been you have a business process, whether that's a real business process, and it almost always was, right? Software is designed to help humans. So there were humans in place, they were doing things, and that resulted in a business process. However, that emerged, obviously it emerged. Doesn't really matter. You want to know what that is and then emulate it in the computer so that the computer can automate the boring parts so the humans can, take a lunch or whatever. Now, this is all how it was supposed to go, right? So the reason why you have a rapid application development language is so that, or process, is so that you can use an easy high-level language to actually emulate the business process and show it to the business users and say, you said this is what you want. Is this how it's supposed to work? Like, is my understanding correct? And more often than not, the understanding of the project manager or whatever development team was roughly correct. The problem was that when the business users went to go do that, they left something out. Why? Oh, well, because Mabel over there, she's the only one that runs that process and she only runs it once a month, but it's the most important process in our business. Oops, nobody asked Mabel. Or when they asked Mabel, she didn't think, oh no, this is the one most important process. I only do it once a month, so I don't think of it all the time. That's actually why rapid application development was pondered, right? Was adopted. And you may say, well, Mark, that's great, but now we can develop whole things in a RAD language, and it worked great. They don't scale. They have lots of problems. There were fixes for that, like microservices, which don't actually fix the problem, but actually create other problems instead. And that's what happened, is we're using rapid application development as the final process, when in fact it was just meant to get the business users working with something so they found all the flaws in their understanding of their own process, right? And then as the design and implementation went on in a backend language like C or C++ or one of the Lisp or whatever language, COBOL, didn't really matter, right? That would be correct. And it's correct because you have the users actually using the stuff. It's not whiteboarded. It's not sitting in a flow chart somewhere. They're actually using a mock-up version that doesn't scale, and it's not supposed to scale because you're writing the real code in the backside over here, right? In a real programming language, not one of these foofy modern languages. And then what happens is you have better software. But they divorce it from that process, right? They divorce the rapid application development concept from the purpose, from the telos. And then what happens is now we're just designing everything in rapid application development style languages, and it's all garbage. And it's not done with the business users in mind. It's just done to get product out the door quicker. And so you substitute the mock-up language for the real language, and the design phase gets collapsed into nothing and goes away. And the software engineers just hit the ground running, write as much code as they can, right? But then that doesn't scale because without design, you can't scale. Like, it's impossible to scale something unless you design it for scale. And you have to design it at a specific scale. And when you change scales, you have to change your design. Your architecture actually has to change, right? In the same way that if you want to build a building, like a one-story building, that's fine. You can build it out of wood. Two-story building, you can still build it out of wood. Three-story building, you can probably build it out of wood, but it's actually better in brick. But you know what? You can't go too high with brick. If you want to build a skyscraper, now you got to use concrete and rebar, right? It's just buildings, right? But at scale, the materials change and the design changes because You can't design a skyscraper the way you can design a 4-story building, right? You need an elevator in a skyscraper. You need more staircases because there's more space for people, right? You need different windows. Like everything changes. The hydraulics in the building change. Like everything gets altered. And so scale matters. And when you don't account for scale, you end up thinking you can just rapid application development everything. And you can't. You can't. It doesn't work. You get bugs. That's why all your software is buggy. It's buggy, well, and they don't know how to test anything anymore. That's what happens. Like these things don't scale correctly. And whole businesses go on, and you still hear about it. Like, oh, we had a big day on the crypto market and our exchange collapsed. Yeah, that happens. Oh, big first day at the subscription service for our new video platform, and it failed, right? Oh, we launched a new documentary and our entire infrastructure fell down. Of course it did. It wasn't designed correctly. Oh, our e-commerce site worked until Black Friday. Boom. Oh, our new register software that doesn't need an NCR custom terminal but runs on PCs failed completely on Black Friday. These things are happening all the time, right? All the time. Oh, we put a new billing system in place for the entire city or water system, and it failed. Yeah, and then it took us a year to fix it. Yeah, that happens. These are real stories from actual events that I actually witnessed or heard about from somebody who was actually there. This is happening all the time with increasing frequency. And that's why it's important to pay attention to, well, what is the purpose of this thing? You can't just use rapid application development because you have it. You need a reason, and that better be a good reason. The reason better match the purpose of the object or the system or the process. Otherwise, you're going to have a catastrophe, and that's the hell we're living in. Everyone's trying to use something for a purpose other than the purpose it was designed for, and that doesn't work. And it seems to work for a long time until it fails completely. And when it fails completely, you're doomed. Like it's over. You're finished. And that's the problem. And lots of businesses suffer from this all the time. I've been on dozens of projects that had this problem. They're just like, I would tell them, oh, that's not going to work. And they're like, no, it's definitely going to work. And lots of weird things happen. So, for example, if you're running a Java project, and I was working on this Java project years ago, and you say, oh, it's really slow, we're going to add more memory. And I don't know how it is with the latest version of Java, because they switched their whole development model for Java, release model for Java. They're not releasing stable versions anymore. But the way the garbage collection system worked is basically it was limited to about 4 gigs. For some applications, you could use 8 gigs of memory. But past 8 gigs, the garbage collection for almost every type of programming within Java doesn't work. So if you allocate 8 gigs of memory to a Java JVM, the odds that it's going to be fast at all are pretty low. There are some corner cases, but they're very rare exceptions. But if you have 8 gigs and you go beyond that to speed it up, it'll get slower every time. There's a mathematical formula to calculate this, by the way. I'm not making this up. There's actual math behind this. And the reason why, roughly, is because if you're allocating that much memory, you also have to unallocate that memory. And that's very hard to do efficiently if you have a bug, right? Like a memory leak, because you can have memory leaks in Java. It's actually very easy. You just won't see it until you run into this problem. So what happened was the team I was working with said, no, we want to double the memory. That'll speed it up. And I said, that's not going to speed it up. It's going to get slower. And they said, look, Mark, you've always been right in the past, but we know for sure you're wrong this time. And I'm like, okay, we'll double the memory. So they doubled the memory on the machines. And the first thing they did is say, all right, well, the machines have the VMs have the double the memory. We're all set. We're good to go. And I said, nope, hold on. You've got to change your JVM memory settings. I'm like, oh, yeah, you're right. No, we absolutely have to do this. Now, this is a good indication that they didn't know what they were doing because they didn't understand that increasing memory on the server doesn't affect the Java JVM at all. You have to tell it to use that additional memory, right? They didn't understand that. Okay. So it's a good indication they didn't know what was going on. So they did. They increased it to 16 gigs. And the load time, it more than doubled. It didn't quite triple. And they were flummoxed. And I said, I knew that was going to happen, and I warned you guys. And they were like, oh, we don't understand. It's more memory should be faster. No, not if you have to deallocate that memory, because you're allocating, unallocated, allocating, unallocated. The real question is, what kind of an application are you writing that you need 16 gigabytes of memory active for? Because there's almost no applications that actually need that kind of memory allocation in the moment. I mean, there's some big data exceptions when you're doing huge chunks of data, but that they were doing transactions. They weren't doing data analysis, large scale data analysis. They were working with what I would consider a tiny data set. They thought it was huge, but when you're loading 200 meg files, you shouldn't need gigabytes of memory to process that ever. There's no mathematical condition where that's possible. So they brought it all back down. I explained to them how to fix the problem, which they didn't listen to the first time, and they fixed it. But they didn't understand, because of the rapid application development, the fact they didn't design anything, and the fact that these newer languages do the garbage collection for you, and so they hide all the memory leaks, that they had a memory leak problem. And they were able to pare it down and mostly fix it. But it took their best engineers off of the design and mentoring work, working on that for a while to do just that, right? Because it's very hard work to do, actually, at the end of the day. So you can see the way in which things are unexpected at scale. Oh, we'll just double the memory and it should get twice as fast. And instead it gets more than twice as slow. It's not intuitive. Scaling is one of those tricky things. And groups don't scale, right, the way you expect. You can't scale things up from quantity one. That's the well-known problem in computers, right? The plus one problem. We're dealing with one entity is vastly different in programming than dealing with 1 plus 1 entities, right? And that isn't so different from, the next n, where n is a relatively low number, but once you hit like 1,000, a lot of things don't scale. Sometimes that's 10,000, sometimes it's 100,000, but almost nothing scales well between, we'll say, fast at 1 to 100, fast at 1 to 1,000,000. Almost no algorithms do that well. There are some exceptions, but they're rare. They're very rare. That's the problem. You can always point at something, oh, it's an exception, therefore you're wrong. No, that's a corner case. Everything is corner cases. And that's the problem that we're seeing. Like, we're not recognizing that anywhere. The matchup between what you're doing, the telos, the purpose, and the object, like, what can the object handle? Can it handle that at scale? Or, and you see that all the way up into ethics and morals. Well, I know I can look at a situation and tell whether or not someone's doing good or bad. Hey, look, maybe you can. Like, I'm not going to say you can't. But can you do that for things you're not involved in or aware of? Like, if you weren't there, can you tell? And that's where it breaks down, right? It's like, oh, okay, well, then we need to know how to gather the information that isn't the information of having somebody there, like you, to be a judge who thinks they're impartial, but you were there, so you're obviously not actually impartial. But we'll set that argument aside. This matters. This scaling matters, because now you have to rely on a bunch of things that aren't, I was there and I know right from wrong. It's like, oh, so justice itself doesn't scale, right? You have to build in systems at different scales to account for justice. And when you scale it up, it goes horribly wrong. I mean, I've been in court cases before. I'm in one now. It's just terrible. Like, 5 minutes. Here, read this. This is a contradiction. We're done. Nope, can't do that. Oh, here are the rules. You can't do this. They did this. 10 minutes should be over. Nope, we got to go to this big court case for no reason. It's crazy. It's absolutely crazy. And that's the problem. We're not recognizing purpose anymore. We're not recognizing the limitations of scale, the constraints of scale. We're not recognizing if you do something, if you use a tool for something that it wasn't designed to do, it may not work well. It may seem like it's working. Like, you can bang a nail in with a rock, right? You can put a screw in a wall with a hammer. I've done it. It's not recommended. It doesn't work very well. It seems to work. Sometimes it works well enough. I mean, I've done it. So I know it works well enough, but it's not good. And that's really the problem. And you see it in computers, and you see it everywhere else. It's just spreading out. This postmodern anti-structuralist meaning crisis is everywhere.